Math 2414, Calculus with Parametric Curves, Video 2, Horizontal and Vertical Tangent Lines. It occurred to me as I was prepping this video that the graph I sketched in the previous video, the one by hand, not the one in Desmos, I don't think I sketched it correctly because when I drew it, it looked a little something like this. And I think it went too far over to the left. I haven't rewatched that video yet because it's still processing, but regardless, the graph does look like it's tangent to the y-axis. But when you studied Calculus 1, one of the big uses of the first derivative was it helped you locate high and low points on a graph because the derivative was measuring the slope of the tangent line. And if the slope of the tangent line was 0, then you had a candidate for a high or a low point, a local maximum or a local minimum. A slope of 0 didn't guarantee a high or low point because you could flatten out and then keep going in the same direction. But it was a place to look where the derivative was equal to 0. But what about for parametric curves, locating vertical and horizontal tangent lines? Because we seem to have some here. It seems like there's a horizontal tangent line at the top of this curve. I missed it a little bit, but you know where I'm talking about. And a horizontal, well, that one's even worse, horizontal tangent line at the bottom down here. And it also looks like there's a vertical tangent line over here, which of course I drew horribly. It's a little bit better. But the question is, how do we locate them in terms of parametrically defined curves? Recall that the curve here was x equals t squared and y is equal to t cubed minus 3t. 3t. So what would it mean to be a vertical or horizontal tangent line in terms of the derivatives of these parametric equations? Well, if you think about it, the derivative of something just calculates its velocity. And so when we calculate something like dx dt and get 2t, or dy dt is equal to 3t squared minus 3, we can think of that as trying to calculate the velocity in the correct direction. For example, the dx dt measures the velocity in the x direction. In the x direction. We'll make that x look like an x and not a y. And dy dt measures the velocity in the y direction. So let's think about what these points would have to do when they hit a vertical or horizontal tangent line. And we're going to go into Desmos to look at that. Let's turn off that tangent line from the previous problem, and let's slide this point around. Now, I think we can all agree that there's a vertical tangent line at the y-axis. So I want you to think about what the point's velocity is doing in terms of the x as it gets closer to that tangent line. Let's back it up over here. All right, point's coming in. And again, just focus solely on its x coordinate. And to help you with that, I've got some extras here. Let me see if I can remember which one of these it is. Nope, it's not that one. Oops, turned them all on. Didn't mean to turn all those on. 1 second, folks. I've got this set up already. I just got to find it. Nope. Nope. I thought I had it set up. Maybe it's down here. Nope. Nope. Well, shoot, where'd the thing go? It's all right, I can set it up real quick. We want the vertical line. X equals the coordinate of that point, and the coordinate of that point is just f of c. So we want x equals f of c, but we only want it between 0 and the y coordinate, which is g of c. You don't have to worry about what I'm rambling about right now. Just know that the more you play with Desmos, the more you can get it to do what you want. What I'm having it do right now is draw a line from the x-axis to the point on the graph. I just have to set up 2 cases, one when the point is below the graph and one when the point is above the graph. Okay, so let's do this. Let's make these dotted black lines. And same thing here. Okay, sorry to take the time to do that, but let's zoom in on this for a second. And let's go back to the slider. And remember, what we're doing is we're looking at the point's x coordinate, but I'm projecting this point to the x-axis. So look at the point where, 1 second, folks. Look at the point above the red point where it touches the x-axis. In this case, it would be the point c, 0. No. f of c comma 0, excuse me. There it is. And let's put it in black. So I want you to watch the black point as the red point makes its journey. The black point is going to be, well, I can animate it. The black point is going to head towards the, whoa, it's going a little fast there. Let's slow it down. Okay. All right, let's continue. The black point's going to start coming in and heading towards the y-axis, but it's going to bounce off it and turn around. And remember, what we're trying to ask is, what do we know about the derivatives when we hit that vertical tangent line? So let's back it up a little bit, and we'll animate it one more time. Just think about this black dot's velocity, since it's only moving in the x direction. It slows down and turns around. But what's its velocity when it turns around? Well, assuming it's a continuous function, which it is, all of these are continuous, as that point hits that vertical asymptote, it's got to come to a halt before it turns around. That means its velocity in the x direction has to be 0. So what does all that mean? That means the following. To find the t-values of vertical tangent lines, we need dx dt to equal 0. So just like in calculus 1, when you put a derivative equal to 0, and I bet you can guess what the next line is going to say. To find the t-values of horizontal tangent lines, then, well, let's go to the Desmos real quick. So for example, at, looks like there's a horizontal tangent line at y equals 2 right there. So think about this dot, and I'm going to turn off everything related to where it is in the x-axis. Think about this dot as it approaches that black line up there. What's its velocity doing in terms of moving up and down? Well, at the top, it's got to hit a vertical velocity of 0 because it's got to come back down. So as the point hits the tangent line up there, it has to come to a stop in the y direction. It's still moving in the x direction, but vertically speaking, it has to rise, stop, and then come back down. So when you have a horizontal tangent line, that's when dy dt is equal to 0. So to find the t-values of the horizontal tangent lines, we need dy dt is equal to 0. I'm going to pause the video and give you a chance to figure out the t-values where we have our vertical and horizontal tangent lines. All you have to do is put the correct derivative equal to 0, and that'll give you the t-values. But then I'm going to follow up and ask you to find the actual points on the graph where there's a vertical tangent line and where there's a horizontal tangent line. So think about how to do that, and we will resume after this brief pause. All right, let's see what we get. For the, well, let's codify which derivative we need to put equal to 0 to find which tangent line. Oh, we already did that. You'll have to forgive me. What was a brief pause was actually almost 1 hour for me while I attended a meeting. Okay, so if we want to find the, I'm sorry, I got to fix this typo. It's driving me crazy. Come on, there we go. To find the t-values of vertical tangent lines, we need dx dt to equal 0. And in the previous slide, we had dx dt was equal to 2t. So this will be pretty easy for vertical. For vertical, we need dx dt, which is equal to 2t equal to 0. But if you solve that, you get t is equal to 0. And for horizontal, we got just a little bit more work to do because dy dt, which was 3t squared minus 3, is quadratic, which means we got to do a little bit of factoring or quadratic formula, but this is easy to factor. We could also just straight up solve for t. Why don't we just do that? If we add 3 to both sides, we get 3t equals 3. Excuse me, we get 3t squared equals 3. If we divide both sides by 1, we get t squared is equal to 1. And if we square root both sides, we don't get t equals 1, we get t equals plus minus 1. So we can say that we have a vertical tangent line when t is equal to 0, and we have a horizontal tangent line when t is equal to plus minus 1. So where on the graph is this? Let's go to the graph in Desmos, since it's a little bit more accurate than my hand-drawn graph. All right, so I'm going to drag the slider around. Let's animate the point. Oh, the point's already animated, excuse me. Let's drag the slider around and try to figure out where each of these t's are. Actually, we don't have to guess, but let's just think. So at the top, we clearly have a horizontal tangent line, and that's at the point 1, 2. Well, what does t equal there? Well, we don't have to guess because we can just figure out. Same thing for the, well, for the vertical, there was only one vertical tangent line, and that was when t is equal to 0. And we had 2 horizontal tangent lines at the top and 1 at the bottom. One when t was equal to 1, one when t was equal to -1. But which is which? Let's find out. All we have to do to find the actual points is go back to the parametric equations. Hold on, folks. Go back to the parametric equations and stick in t equals 0 and t equals plus or minus 1. So when t is equal to 0, we have x is equal to t squared, so 0 squared is equal to 0. And we have y is equal to t cubed minus 3t, so 0 cubed minus 3 times 0, which is 0. So as expected, t equals 0 was at the origin, and that's where we had our vertical tangent line. For t equals 1, we have x equals 1 squared. And in case you don't have it written down, remember that x is equal to t squared, and y is equal to t cubed minus 3t. So when x is equal to, when t is equal to 1, x is equal to 1 squared, which of course is 1, and that's purple. And y is equal to 1 cubed minus 3 times 1, which is -2. So t is equal to 1 at the point 1, -2. Maybe a little counterintuitive because you might have expected it to be at the top of that curve instead of the bottom. And similarly, when t is equal to -1, that implies that x is equal to -1 squared, which is 1. And y is equal to -1 cubed minus 3 times -1. Watch your signs. That's equal to +2. So the point where t is equal to -1 is actually at 1, 2. If we go back to the hand-drawn graph, then let's get rid of these tangent lines because they're kind of blurring where the axes are. And I can get rid of that one. Then t is equal to 1 was down here. Didn't mean to make that go away. This is where t is equal to 1. T is equal to 0 over here. T was equal to -1 on the top. And so we actually have an orientation like this. But I think we kind of already saw it when we played with Desmos before. So to summarize, if the question is to find the locations of the vertical and horizontal tangent lines, you simply put the correct derivative equal to 0. Let me check something real quick. And we're going to bring that up later, but it does bring up a question. What happens if both derivatives are equal to 0 simultaneously? For example, and this is a totally different set, well, not totally different. If we had x equals t squared and y was just equal to t cubed without the minus 3t, then dx dt would be 2x, dy dt would be, not 2x, 2t. dy dt would be 3t squared, but when t is equal to 0, we have both of these derivatives equal to 0. dx dt is equal to dy dt, which is equal to 0. Pretty easy to see if you put 0 there and there. So what happens when both derivatives are 0 simultaneously? Well, we'll check that out in the next video.